Okay, so continuing on here, number 4, all atoms have a full octet in the molecule moscovium oxide. Moscovium is right here, Mc. So true or false? Well, we need to draw the Lewis structure of this. And so in order to figure this out, and first step, right, we want to figure out if it's satisfying the octet rule. So that's why we use the Lewis structure business. So first step in drawing out the Lewis structure is come up with the number of valence electrons. Moscovium is in the same column or family as nitrogen, and nitrogen has 1, 2, 3, 4, 5 valence electrons. There's 1 in moscovium. Oxygen has is 1 to the right of nitrogen, so it's going to be in group 6. So there's 11 valence electrons. And right away here, if you think about this, you have an odd number of electrons. And so if both atoms are going to have equal number of electrons and have an octet, that has to be even. Okay. So right away, just based on the fact that we got an odd number here, you could, answer correctly that this is false. But let's go and show how this would work with a Lewis structure, right? So we'd have our moscovium and we have our oxygen. We're going to tie those together. And then we're going to try to satisfy the octet rule the best we can. So we have 2 electrons accounted for, 4, 6, 8, 10, and then 11. Okay, we could put that on the most electronegative atom. Moscovium is really down on the periodic table, so it's not going to be very electronegative. And so we'll put it on the more electronegative atom, the oxygen, but this is not satisfying the octet rule. We're going to have to start making multiple bonds here. So we're going to have to bring in this lone pair here to at least get us into a better situation. And I mean, you can see this still isn't going to satisfy the octet, okay? So 2, 4, 6 for moscovium, 2, 4, 6, 7 for oxygen. We're getting closer. We can bring in another lone pair and try to make a triple bond. And if we do that, moscovium is going to be happy, 2, 4, 6, 8, but oxygen is going to have 2, 4, 6, 7. So it's never going to work when you have an odd number of electrons. All right, so number 5, molecular orbital theory is less accurate than Vsepr. This is, I said I'd only test you on very basic things with molecular orbital theory. And so this is definitely false. Molecular orbital theory is way more accurate than Vsepr. And in fact, there's a lot of situations that Vsepr just gets wrong. It predicts the geometry wrong, predicts properties wrong, predicts shapes wrong, and so that's false. All molecules with a central atom and 4 surrounding atoms are tetrahedral, okay? And so let's think of some examples here, and that might be the best way to go about this. But so, maybe methane. Methane we can draw the Lewis structure of this, and methane the Lewis structure would look like this, satisfying the octet rule. For carbon, 4, duet rule for hydrogen. Carbon's in group 4, and we have hydrogens in group 1. There's 4 of them, so there's 8 valence electrons, and our structure here does have 8 valence electrons. That will be tetrahedral, right? What is the steric geometry? Steric geometry is 4. Molecular geometry is 4. But molecular geometry is tetrahedral because there's no lone pairs. But what if you have something that has a lone pair? This is where it's going to break down, right? Because you could still have 4 terminal atoms, 4 surrounding atoms like that, but not be tetrahedral. So an example would be xenon tetrafluoride. Let's do the valence electrons for that. Xenon is a noble gas, 8 valence electrons. Fluorine is a halogen, that's 7 valence electrons. There's 4 of them. That's going to get you 28 plus 8, that's 36 valence electrons, right? And so you put down your central atom. So this is tetrahedral, by the way. methane. You put down your central xenon and you put your fluorines. Oops, it should be a fluorine, not an iron. And you want to satisfy your octet rule for the fluorine. If you do that, 2, 4, 6, 8 for fluorine, there's 4 of them, they're all identical. 8 times 4 gets you 32. You need 36 valence electrons. So this is what I'm talking about. This is an example where you have lone pairs on the central atom, but you still have 4 surrounding atoms. What's the steric geometry then? Steric geometry, well, the steric number is 6. So this is based on the octahedron, and the molecular geometry, when you have 2 lone pairs, you take off 2 of the caps of the octahedron, that gets you square planar. Okay, so not tetrahedral. So that's an example where this, would definitely be false. So this is false.